Our next speaker is Clifford Cheung, who is a theoretical physicist at Caltech. He received his PhD in physics from Harvard in 2009 before joining the faculty at Caltech. He's a recipient of an early career award from the Department of Energy and is a fellow of the Alfred P. Sloan Foundation. Among other things, Professor Cheung is interested in the study of scattering amplitudes, which are fundamental observables encoding the dynamics of interacting particles. At a basic level, these efforts are dedicated to understanding why the laws of physics are as they are, in particular discerning which aspects of the natural world are inevitable purely from consistency with basic physical principles. Please welcome Dr. Cheung to talk about amplitudes from gluons to gravitons.
Great. So before I start, let me first give my enormous thanks to the organizers, Glenn and Brian, for inviting me here to speak today, but much more importantly, for organizing this absolutely wonderful conference. I have to say that in the last couple of days, it's been fascinating, but also incredibly inspiring to hear all of the firsthand accounts of the creation of the Standard Model from the very individuals who pieced it all together. Obviously, I come from a much younger generation for which a lot of this history is almost mythological. So it's been absolutely eye-opening, and it's hard to describe how amazing it's been to be even in the same room as so many of my scientific heroes, honestly. Now, this morning's session, I guess nominally is entitled New Developments. So I thought I'd start by just echoing a common refrain we've heard in previous talks, which is that the Standard Model, in spite of its immense success, is certainly not complete. We know this because of overwhelming experimental evidence for things like dark matter, cosmic inflation, baryogenesis, and so on. Now, in spite of all that, in this talk, I'm actually not going to be giving you any interesting stories about beyond the Standard Model physics. I'll be focusing on bona fide Standard Model physics, in particular physics describing the dynamics of gluons, pions, gravitons, and so on. Now, a priori, it would seem like there's not very much new to learn in this subject. I mean, we have the Lagrangian for these theories due to the immense efforts of individuals in this very room. But what I want to tell you about is how recent developments in theory have revealed structures, really hidden structures, inside the Standard Model and inside quantum field theories in general, which as of yet have no discernible explanation from the point of view of Lagrangians or Lagrangian symmetries. So the way these structures were really discovered was by studying scattering amplitudes. So I'll be updating you on some developments in a quite young but growing research program, which is sometimes called the modern S-matrix program. So I'm sure this sounds familiar because it should. It's an unabashed reboot of the analytic S-matrix program from the 60s and 70s. Famously, this was a contender for the strong interactions before it became abundantly clear that quantum chromodynamics was an elegant and beautiful and, most importantly, correct description of that physics. But of course, there was some lessons to be learned from the S-matrix program. One outgrowth was string theory, famously. What I want to tell you about, though, is how some of the tools and insights from that old story have been kind of retooled to understand quantum field theory in the perturbative regime. Okay, and much of this work was pioneered by individuals like Zvi Byrne, Lance Dixon, and David Kossover, and many others, who kind of took this picture and ran with it in a different direction. And now it's kind of taken a life of its own. So if I had to kind of summarize what the point of the S-matrix program is, it's essentially to sidestep the need for a Lagrangian. After all, why do we define a Lagrangian? What you do is you really start with some set of physical principles, like Lorentz invariance and locality. You hard code that into, say, an action, and all the parameters not fixed by physical principles are free parameters. Okay. So then our experimental colleagues can measure those parameters, and then we make new predictions by, say, computing Feynman diagrams and repeating the cycle. Now, of course, what you get out is what you put in. So by logical inference, it should be possible to go directly from whatever physical principles you stated to the final observables, which for the purposes of this talk will be on-shell physical scattering amplitudes. Okay. So in short, the S-matrix program of old and of new is about trying to skip this middle step. Okay, which should naturally feel extremely imprecise, or at least like a pipe dream. But as I'll tell you, it's actually very mathematically concrete procedure by which you can go from a set of principles to the final answer directly. Now, before I do that, I think I need to address why one should even bother. After all, we have the Lagrangians for these theories. I've told you I'm working in the perturbative regime, so you can just compute with Feynman diagrams, and that's certainly just true. But just one pragmatic downside about that is that Feynman diagrams tend to be immensely complicated. Anyone who's computed them knows this. Even for the kind of next to simplest processes, that's true. So here, this is some gluon scattering amplitude at tree level. You could compute this using Feynman diagrams, and you get this expression, which I'm kind of showing you for a dramatic flare. But each of these smudges is a very complicated, itself a function of the polarizations and momenta. So it's long, but of course it gives you the correct answer. Now, of course, an extremely well-known fact is that when you restrict the external legs, the external gluons to physical configurations. So what I mean by that is a configuration of momenta which add up to 0, conserving momentum, which are on shell and also have some helicity associated with them. This huge expression is actually vastly simplified. So for instance, if I restrict to all plus scattering for the helicity amplitude, this collapses down to 0, which tells me that this expression was just a very complicated rewriting of 0. For the mostly plus, I also get 0, and famously, at 5 point, the only non-vanishing amplitudes have 2 minuses or 2 pluses. This is a celebrated Park-Taylor formula, which generalizes these so-called MHV amplitudes to actually all numbers of gluons. So the point here is really just that this answer is very simple. I've written it in terms of so-called spin or helicity variables. In case you're not familiar with them, these are really just a rewriting of the external form momenta. That's all they are, just a re-expression of the same data that's inside p mu. Okay? It won't be that important, the details of this. Now, the upshot of this is that there is a very complicated intermediate step, which is the Feynman diagram, but the final answer is simple. So a question might be, why is it simple? Is there a way of writing down a theory which goes directly to the simple answer? And we'll see that the answer is actually yes. Now, this is not just a property of gauge theory and Yang-Mills. You can ask the same question about gravity. So you could study graviton scattering amplitudes, which are basically defined as weak field gravity waves interacting non-linearly in a flat background. Of course, the Feynman rules for this were written down, again, very long time ago by DeWitt and by Feynman. And you see the same kind of small miracle, which is that there are thousands upon thousands of of terms. Many Feynman diagrams you sum at 4 point. But when you restrict to the external legs being physical, then it collapses down to this monomial expression. Okay. So what's the reason for this complexity? Well, a little bit of the irony here is that some of this complexity is coming from the implicit gauge symmetry in the Lagrangians we use. So of course, gauge symmetry is a beautiful geometric picture, which has given us so much insight about the underlying structure of these theories. But of course, its kind of defining property is that physical quantities like electric fields and magnetic fields are gauge invariant. It doesn't show up in those observables almost by construction. Oh, by construction, I should say. And on-shell amplitudes are no different. So one kind of pragmatic way to think about gauge symmetry, just a different perspective, is that it's a way of manifesting two physics properties which we know are true at the level of every step in our calculation. So we know that Lorentz invariance and Poincare invariance is a symmetry of nature. We know that locality is. So we hard code that into a local Lagrangian, which exhibits a manifest Lorentz symmetry. This forces us to introduce a 4 vector to describe the photon. Of course, that has 4 degrees of freedom, and as was discussed before, we need to introduce gauge symmetries pragmatically, if you like, to bring us down to the 2 physical polarizations of the photon. Now, of course, that's all a beautiful structure, which has given us immense insight. But there's a cost to that, which is that when you compute the amplitudes, they have enough terms to satisfy these Ward identities to instate this symmetry. In other words, this gauge symmetry is hard-coded inside the way we compute Feynman diagrams normally. What this ends up doing is giving you an explosion in numbers of diagrams and also numbers of terms when you compute. So this is just an imperfect measure of how complicated an answer is. But if you compute with Feynman diagrams the amplitudes in say, a gauge theory, even at 8 point, you'll get something like 34,000 diagrams. But as I said before, there's a simpler path. Okay? Something I'll tell you about in a bit are a method called recursion relations, pioneered by Brito, Cacciazzo, Feng, and Witten, which give you a kind of different formulation of the theory that does not use a Lagrangian, but results in mathematically equivalent expressions which have merely 20 terms, say, at 8 point. Okay, so these two expressions, one 34,000, one at 20, are equal, but one somehow pops out of this calculation in a more compact form. So the question is really just, does this mean something? Is this an accident? Is this telling us something deep? Now, you might gather from this that this is all merely a problem with theories with spin, with maybe gauge symmetries, diffeomorphism invariances, but it's actually endemic to all QFTs in a particular sense. So I'll even give you an example for the case of scalar field theories. Okay, you think, okay, there's no spin, no gauge symmetries. What could go wrong? Well, consider the following Lagrangian. Okay, it's got some d phi squared prefactor, and then an infinite set of terms. Okay. Here, lambda 1, lambda 2, lambda 3, and so on have absolutely no relations amongst them. Now, if you just computed scattering amplitudes in this theory, 4 point, 5 point, 6 point, you'll find that they all vanish on shell. For physical external configurations, all these amplitudes vanish, which will look like a complete miracle if you do the calculation. You'll find many, many Feynman diagrams that add and in the end conspire to be 0. Now, that may be surprising, but of course, those of you who know classic reparameterization theorems in QFT know this is actually kind of obvious, because you can perform a field basis transformation, which takes this Lagrangian and maps it to this Lagrangian, which is that of a free theory, for which the amplitudes are trivially free, trivially 0. Okay. Now, while this kind of fact is quite surprising, it should be even more surprising to you because it's not a symmetry of the Lagrangian. The statement is that you can do a transformation of this Lagrangian that changes it, and that actually doesn't modify the on-shell scattering amplitudes. There's a close cousin of this you know from even classical physics. Maybe I'll try to ground this in something a little bit more intuitive, which is that you can think about a Lagrangian in Cartesian coordinates for, say, a classical particle. There's an operation you can do on that Lagrangian which changes it. That operation is to go from Cartesian to polar. That is not a symmetry of the action, right? It changes the Lagrangian mechanically. But of course, you know that if you map properly observables in the two different bases, you get exactly the same expression. So in other words, these objects, phi, the fields, they give us phenomenal intuition, but they're also, at the end of the day, integration variables at some fundamental level when we compute physical objects. Okay. So there's a downside to this, which I want to emphasize, which is that there's actually many, many Lagrangians that lead to the same exact observables and the same amplitude. Okay, so thus constitute the same theory. Why is that? Well, you could have started with your favorite Lagrangian for a given theory, and you could do a field basis transformation to get an infinite set of different looking Lagrangians. Okay? But I've just told you that those are actually all leaving the amplitudes invariant because they describe the same physics. Now, what's unfortunate about that is that it may be that all the structures you might care about are not manifested in your particular favorite Lagrangian. Okay? Maybe you're even using Cartesian when there's some secret spherical symmetry in the system you care about. And what I want to tell you about is structures that I think are just not manifest in the kind of classic Lagrangians we are used to seeing. And my talk will be kind of split between two basic points. One is that by studying scattering amplitudes in and of themselves, you can actually learn a fact about the immense rigidity of quantum field theory. So these are facts you can, of course, understand from the classic ideas about quantum field theories, gauge theories, renormalizability. That's all there. But you can kind of re-derive those ideas in a different way. Okay, and the way here is to start with some set of physical principles like Lorentz invariance and locality and go directly to the scattering amplitude. Okay, and let me tell you precisely, or at least in a broad brush, how you do that. It's, the picture is actually quite simple. Okay, so what you do is you define an ansatz function which spans the space of all possible S matrices that you could ever have. Okay? So of course this needs to take some set of assumptions. So let's say we're interested in tree-level scattering amplitudes. What you do is you define an ansatz of rational functions, which are functions of the external kinematics. You would then impose some set of physical conditions. Okay? So this would be like Lorentz invariance, factorization, properties that have some underlying physics. Now, when you do that, your ansatz will go from having some number of free parameters to a smaller number. Okay. If that smaller number was, say, 7, let's say, then you would have discovered the S matrix for a theory with 7 coupling constants. If you find instead 1 free parameter, then you've discovered a 1-parameter theory. Furthermore, if you discovered no solutions, if you discovered that there was no ansatz consistent with some set of physical principles, then you've actually ruled out the theory. Okay, so this allows you to, in the abstract, actually rule out theories without even knowing whether they have a Lagrangian, because you've shown the physical principles to be mutually inconsistent. Okay. So this will be kind of a cute way of kind of organizing and learning about QFTs we know, but also ruling out QFTs in the abstract. Now, if we were just in the business of reproducing old facts about QFT, it would honestly not be that interesting. But the real meat of this program, at least in my mind, is that new things, genuinely new things, I think, have been discovered. And I'll talk about kind of two aspects of this, one which is a hidden duality amongst QFTs, and another which is a set of unifying relations amongst QFTs. And these will connect the dynamics of particles like the gluon, the pion, and the graviton. Okay, so let me start at this first section. So there's of course kind of two physical principles that I've been telling you kind of about in each slide, and I'm going to take these as the inputs. These are physical assumptions that I just want to take, okay, which is Poincare invariance and locality. To our knowledge, experiments agree that these are good symmetries, at least far from curvature, to very good approximation. Now, we're used to thinking of gluons and gravitons as perhaps examples of self-interacting massless spin 1 and spin 2 particles, but they're unique, okay? If I tell you that I have defined a theory of massless self-interacting particles of spin 1 and spin 2, these are actually the only cases allowed, provided that you assume, say, dimensionless coupling in this case, okay? Which is, of course, me inputting renormalizability in some kind of oblique way. But the way we derive this is not by writing down a Lagrangian and talking about gauge symmetries at all. We really just take functions built from those spinor helicity variables I showed you before. We write down a completely arbitrary function of them, and then we demand that they have the right dimensions and also the right so-called helicity weight to accommodate these amplitudes. Okay, so I can't show you the precise details here. You can look at my TASI lectures if you like on the archive if you want all the nitty-gritty details. But you can do this, say, for gluons and gravitons, and you can uniquely construct the 3-particle scattering amplitudes, which are given here and here. Okay? The claim here is that these are the only Lorentz invariant quantities of the right mass dimension to even be these objects. Okay? As it turns out, these are actually even non-perturbative. So I haven't made any assumptions about tree or loop in this discussion even yet. Now, one thing I want to point out is already a structure emerging, which is not, at least not obvious from the point of view of a Lagrangian, which is that if you take the gluon amplitudes and just square them, blindly square them, you get the graviton amplitudes. Okay, if you've computed, if anyone's computed both of these, you'll know that the Feynman diagram calculations do not obviously have this structure embedded in them, but this is a fact about them when they are chosen to be on physical configurations. This picture of building the 3-particle amplitude for massless particles was done originally by Benincasa and Conchazo, and it gives us now really the 3-particle amplitude for any number of massless interacting particles. It's also been extended to the particles with mass more recently. Now, this is 3 particles, which is, of course, very simple. We want to go to 4.5 point and higher, and we need, for that reason, some other physical input. That physical input, I'm going to call locality, but at a mechanical level is just factorization. So what do I mean by that? Well, what we do is we define some A4, which is an ansatz function for the 4-point function. Okay? It's defined, again, as some rational function of the kinematics. And we demand the following constraint, which is that when P1 and P2, their sum goes on shell, thus putting on resonance this intermediate leg, this thing factorizes into 2 lower point 3-particle amplitudes. Now, this is just a statement that when you go on shell, this process looks like a 3-particle interaction followed by a particle traveling a great distance in space-time and then decaying, if you like. So we've already known what A3 is in the previous slide. So by applying this constraint, you can deduce A4 from A3. Okay. And you can do this step by step. You can then go to A5 to deduce it in terms of A4 and A3 and so on. Okay. The crucial point here is that the data you're inputting when you do this summation is not Feynman diagrams, because this thing is on a factorization channel. So this thing is on shell and this thing is on shell. So at every single step of the way, you're dealing with physical objects, completely physical objects. Now, fortunately, this has been, there's a way of automating this procedure, which I mentioned before, which are called recursion relations. So in this way, you can take an n-particle gluon amplitude or even an n-particle graviton amplitude and recurse them all the way down to the 3-particle amplitudes. Okay? So just from the 3-particle amplitude, you can actually do this. So as I mentioned before, from this construction, you can not only rediscover classic, beautiful old theories, but you can rule out theories. Okay? So what you can do is define an ansatz and then assume some set of principles and draw a map in that space to determine which theories are allowed and which are not. So there's a natural axis, a set of natural axes you can draw to kind of produce a map of theories. On the x-axis here is spin, so the spin of the some set of self-interacting particles. On the y-axis, I've defined some parameter rho, whose details don't particularly matter, except that it's related to the mass dimension of the coupling, or equivalently the number of derivatives per particle in the leading interaction. Okay. So it's connected to kind of how derivatively coupled the theory is. And from these basic principles, I think it's hard to see here, or very hard to see, there's actually an allowed region and a forbidden region, simply because you can construct the ansatz and you find no solutions. Now, it turns out that theories that we actually know and love, which show up in the standard model, are kind of cusp cases. So there's actually a line here dividing these allowed and forbidden regions, which is hard to see. I apologize. But gravitons and gluons live on this line, which is a different explanation for why gravity has one parameter. It's a one-parameter theory, G Newton, and Yang-Mills is a one-parameter theory with alpha S. Okay, so this is just a different way of actually getting at that same known fact. Now, these methods can be extended beyond just gauge theories and gravity theories. We can actually also use them to understand effective field theories. Okay? A classic example is the chiral Lagrangian, where I can just recap known facts, which is that, as it turns out, if you assume Poincare invariance locality and one extra ingredient, you can actually build the amplitudes in the chiral Lagrangian. The extra ingredient here is infrared structure, which is an allusion to Professor Adler's Adler zero. Okay? And this is a result that was known a long time ago. Susskind and Fry showed that you could invert the kind of usual picture of starting from QFT and going to amplitudes. And what you can do instead is, so in the usual picture, you take some chiral Lagrangian, you compute amplitudes, and you discover the Adler zero, which is the statement that when you take a pion to be soft, the amplitude vanishes. If you invert the logic, you can instead assume the soft theorem, construct an amplitude which, when a particle goes soft, the amplitude goes to zero, and you can actually derive the chiral Lagrangian order by order. Okay. So that was shown by Susskind and Fry. You can kind of take this logic to the nth level to build a map of effective field theories in a very similar way. Here, rho is, much like in the last slide, just a characterization of the number of derivatives per vertex. Here, this parameter sigma is a characterization of the degree zero you get in the soft limit. And what we find is the chiral Lagrangian here, and actually two more exotic theories, which are, as far as we know, not in the standard model, but have shown up for completely different reasons in cosmology and in formal theory. This DBI is just the Dirac-Born-Infeld model. This is the scalar of it, which shows up in various inflation models, say. The Galilean is something which appeared in theories of massive gravity as the longitudinal mode. There's kind of a lot of interesting quantum field theory just in these objects themselves. And I'm not quite sure what to make of them all showing up together, but this is just what happens. Okay. Now, the upshot of this is that you can, again, automate this kind of construction and build recursion relations for these theories, and this puts theories like pions in the same class as theories like Yang-Mills and gravity. Now, I've drawn these two pictures very suggestively for a kind of obvious reason, which is that there's actually, not only are the theories on this line kind of maximally constrained, in the sense that they're on the boundary of what is allowed and not allowed, there's actually secret hidden dualities mapping them together, okay? That is to say, connections between pions and gluons and gravitons, which are, at least to me, very puzzling. Okay? So I'll tell you first about a certain duality, which is known as BCJ, the BCJ color kinematics duality discovered by Byrne, Carrasco, and Johansson. It's a very close cousin of the so-called famed KLT relations, which arise in string theory due to open string, closed string duality. But this is something which is kind of purely within the regime of QFT. I can tell you much more about that if you like, maybe offline. But the idea is the following. So I'll show you this at 4-point. Okay? That's just what the basic notion is. So if you compute a 4-particle gluon amplitude, you can write it as follows, where there is a color factor, CS, CT, and CU. Okay, these are like the traces of the Lie algebra generators. And then there's kinematic factors NS, NT, and NU. Okay, the N's here contain all the inner products of momenta and polarizations and such things. Now, of course, we know that the color factors satisfy the Jacobi identity. Okay, if you like, let me take that as input, although you can actually derive that purely from the amplitudes picture. But this is, if you like, just an identity. It's automatic. What B, C, and J found was that it's possible to take an amplitude and arrange it in a certain way. In other words, kind of shuffle terms around such that the numerators satisfy this identity. Okay. This is highly non-trivial because the factors here are not, matrices and inner products of matrices. It's really just kinematic functions, polarizations and momenta dotted into each other. So they made this first remarkable, at that time, conjecture that you can write the numerators in a way that exactly mirrors the Jacobi relations of color. Okay. It turns out at 4-point this is semi-trivial, but at 5-point, 6-point this is still true, and it's quite surprising that that is true. They called this a duality between color and kinematic simply because they satisfy the same algebraic identities. Now, that may or may not be impressive to you. What is impressive to me, though, is that you can go further and say the following. They ventured to conjecture that, well, since C and N satisfy the same identities, let me simply take C and replace it with N and see what I get. If you do that, then what you find is a new amplitude which has no color. The color structure is evaporated, and in fact, the kinematic structure is changed because the numerators have been squared. Turns out this is exactly the 4-particle graviton scattering amplitude, okay? Which is, as far as I know, was not obvious in any, it was not clear why that had to be true. This could have just been some completely arbitrary function. Okay. Now, what's much more remarkable than this is that it's not just true at 4-point. Okay, this general picture of squaring gluon amplitudes to getting graviton amplitudes. It's true for all numbers of external gluons and gravitons at tree level. That's a proven fact. It's been verified at various loop orders, and in fact now is used in many calculations actively to simplify calculations in gravity. And furthermore, it's not just a property of gauge theories in gravity. It turns out that while you can take gluons and combine them to make gravitons, in other words, build any n-point graviton amplitude from the square of an n-point gluon amplitude, we show that this is also true for pions. So you can take pion scattering amplitudes at n-point. You can strip off their flavor structures, which are the analog of color, and their product gives you amplitudes in this Galilean theory, which shows up, as I said, in hypothetical models of cosmology. Even more oddly, you can take kind of mixed products. You can take a gluon amplitude, strip off its color. You can take the pion amplitude, strip off its flavor, take their product, and you get the amplitudes in Born-Infeld theory, which is a well-known nonlinear extension of electrodynamics. Okay. So again, I should say this is not conjectural. This is proven. You can check it to 10-point explicitly, even with Feynman diagrams, if you wanted to. But these are understood to be true facts. But the underlying physics, at least in my mind, is still elusive. Why this had to be true. Okay. Now, I think this can actually teach us some new things about even the Lagrangian physics. Okay, so we can kind of work backwards a bit. I've told you that graviton amplitudes can be written as products of gluon amplitudes, and that actually tells you something slightly deep about gravity. Okay. What it tells you is the following. So if you look at the left-hand side of this, it's actually the product of two Lorentz scalars, right? Because an amplitude is a Lorentz scalar. So this has two separate Lorentz invariances, one for this gluon factor and one for that gluon factor. But this thing is, of course, equal to some graviton amplitude. So it tells you that sitting inside the gravity Lagrangian is actually two separate Lorentz invariances. So an exercise you can do, which is kind of cute, is you can just take the Einstein-Hilbert action, and you can just through some work, find a field basis and gauge fixing, which manifests both Lorentz invariances off-shell, even at the level of Feynman diagrams. Okay, so we built some action which has double Lorentz invariance for every off-shell Feynman vertex, and perhaps more surprisingly yields graviton amplitudes which have dual Lorentz invariances, manifesting exactly this doubled structure. Now, this is all kind of high-order theory, if you like, but there could be some kind of more pragmatic output. There's a growing effort in our small community trying to take some of these tools to actually compute things that might be of worth to experimentalists. One of those is kind of natural target is LIGO. Of course, there was this triumphant discovery of gravity waves, which we'll hear about shortly. In order to match Newton. Einstein's theory of gravity, what we need to do is do a post-Newtonian expansion, which at its very heart involves, in the kind of standard methods, computing Feynman diagrams. And as I've told you, there's kind of an interesting shortcut that we might apply in this case. So the idea is whether you could use gluon amplitudes instead, which are easier to compute, square them to get graviton amplitudes as a shortcut to these types of calculations. One thing I don't have a slide for, but I wanted to mention is that this kind of double copy structure, or some vestige of it, has also been identified in classical solutions, where Montero and O'Connell found that you could take Schwarzschild and think of it as a square of a kind of monopole background in E&M. So there's also other connections which we don't fully understand, which happen even just classical field theory. So the last thing I want to tell you about is about a hidden unity among all the QFTs I've talked about so far. And it boils down to this picture. Okay. So let's say that someone handed you the tree-level scattering amplitudes of gravity, all of them, okay, at all numbers of particles. Okay? You don't know how they got it. They have some oracle, but they handed it to you. Okay? And everything I'm going to say here is only at tree level. Okay? It turns out that there is a precise mathematical operation which allows you to sculpt from that set of amplitudes every other amplitude that I've discussed so far. So you can cut out from this object the gluon amplitudes, the chiral Lagrangian amplitudes, and if you like, maybe some of these more exotic amplitudes. And the operation is actually quite simple. The operation is quite simple. So the idea is to take the amplitude and think of it as an abstract function of Mandelstam invariance. Okay? So these are just p.p's, p.e's, and e.e's. The operations which take you from theory to theory are literally just differential operators in the space of Mandelstam invariance. So this is not conjectural. We can prove this and check it, which we did, checked up to 10 point and then proved using recursion relations. But it tells you that somehow gravity is, as I said before, or at least alluded to, is kind of the mother of all theories. And I wanted to emphasize that this vertical axis should not be thought of as energy. I'm not making a statement about unification, granulification, string theory. I'm making a more formal statement about the physical observables in this theory being mapped to these physical observables. Now, there are, again, I think, some lessons we can take from this, which is that essentially facts about gravity will be inherited by these descendant theories through this operation, this very mechanical operation. One fact about gravity, which I just told you about, is that a graviton amplitude can be expressed as a product of two gluon amplitudes. So if you apply the same type of operation, you can learn as a kind of shortcut why pi amplitudes square to these amplitudes in this kind of exotic Galilean theory. So in some sense, this web of copies can be understood in a particular way. Now there's other properties, well-celebrated properties of amplitudes, which also kind of map onto each other through this set of operations. The Weinberg soft graviton theorem describes how an amplitude behaves when you take a single graviton and take its energy to 0. What this mapping does is it actually takes that theorem, that expression, and maps it to Weinberg's soft gluon theorem. And if you apply this again to give you the pion analog, it actually maps to the Adler 0. You can also apply this to well-known subleading soft theorems. So there's the Kroll-Burnett, Low, subleading soft theorems in gauge theories. Also newly derived subleading soft theorems from Cacciazzo and Strominger. And they, again, all map onto each other in this way. Okay? So it's kind of an acute way to actually see connections between otherwise disparate theories, all of which are various aspects of the standard model. Now, everything I've told you is really at the level of the amplitude. But as I mentioned, I mean, the dream that I have is to kind of understand these with every possible tool we have, including quantum field theory and Lagrangians. And we've made just a slight amount of progress in that direction. You can actually kind of reverse engineer some of these statements to the Lagrangian level, giving you some kind of learning some new things about these theories. So this green arrow, let me review. This green arrow was something that allowed you to go from gluon amplitudes to pion amplitudes. You can reverse engineer what that operation is at the level of the Lagrangian. And you find that it does the following. take the Yang-Mills Lagrangian and you apply this mapping, and you get the following bizarre structure, which you can even check explicitly outputs exactly the chiral Lagrangian amplitude. So this is obviously not the usual form of the chiral Lagrangian, right, the one you obtain from looking at spontaneous symmetry breaking, G-H, CCWZ, that whole construction. This is not that non-linearly realized formulation. It's a different one, and one which is truly bizarre. I would love to give you more details about this, but I'm entering probably negative time soon, which is that, well, I'll point out some simple facts about it, which is one, it's cubic. Okay? It's a cubic Lagrangian. Two, it has a number of auxiliary objects in it, okay, which, if you like, are not external states. But what I'm telling you is that if you compute the amplitudes in this, they are chiral Lagrangian amplitudes. Now, there is, as it turns out, also a symmetry this has that the usual chiral Lagrangian does not have. And it has to do with this duality I mentioned before. If you take these three particle interactions and you look at their kinematic structure and their flavor structure, you will find that their kinematic structures automatically satisfy the Jacobi identities at Feynman diagram level. Okay? Which means that there is implicit duality between flavor and kinematics in this Lagrangian. So you can even take this Lagrangian and square it to get a new Lagrangian for those other, that other Galilean theory I mentioned before. Okay, so this is just one minor step, but it gives us kind of a different picture to think about the same physics that we're very familiar with in a different context. So I think I'll conclude now. I did want to emphasize that I've given you only a cross-section and moreover a very idiosyncratic cross-section of the kind of interesting facts that have appeared in the study of scattering amplitudes. But there's really many more small miracles happening here. There are, as an example, there are simple formulas like the CHY scattering equations, which actually give a definition of all the scattering amplitudes in every theory I've talked about to all orders with a very compact set of expressions. There are ways of reinterpreting amplitudes as volumes in the so-called amplituhedron and various cousins. But it's really a program where there's many more questions than answers, which is why I think it's attracted so many young folks like myself who are honestly passionately interested about the dynamics of gluons and gravitons, you know, good old standard model physics. So if I leave you with anything, I want to, in this celebration, just give you my own sense that while I think beyond the standard model physics is something that we need to pursue and understand, we should also not forget that we can look inwards in the standard model, and there could be structures that might teach us something in the long run. So thank you very much for your attention, and stay tuned.
I was wondering if you could actually go up that pyramid also that you're showing, and right. And then maybe a second question also is that I was wondering if this could actually be used in conjunction with ADS-CFT ideas in order to maybe help actually find all the information you need to be able to go up and down that pyramid. Right.
So for the second question, I don't know. I haven't thought about it. I think it would be intriguing. There was a motivation for why we wrote those operators down, which was not just random, but I haven't thought about it. So I don't know the answer to your second question. For the first question, I know the answer is no, because we tried it. And that's why, you know, in the paper, we call this transmutation, going from gravity to other theories, but I think that was the wrong word, because transmutation takes you from, you know, the less complicated theory to the more complicated theory, when it turns out that you can't actually reverse the process. So in some sense, these are differential operators, so you lose constants of integration as you go down. That's a very simple way to see why inverting that procedure does not apply, at least as far as we know. Yes?
I can't resist making a remark here.
Sure.
That we are celebrating 50 years of standard model. Now, 50 years ago, most people were not using Feynman diagram, in particular when you had vector particles or things like such. Mm-hmm. But they use a tremendously much more complicated notation, with starting from the Hamiltonian instead of the Lagrangian. Mm-hmm. Mm-hmm. And then you would get the Schwinger terms, so you don't want to know what they are. Right. Because it was just horrible, just saying that it was extremely messy to do any loop calculation if you didn't have scalar particles. Mm-hmm. And now I'm somewhat amused by your remarks saying that Feynman diagrams are immensely complicated, and you have what is it? Oh, sorry. Yes, the unnecessary complexity in the gauge symmetry makes things simple. This was just completely the opposite. When Feynman diagrams finally emerged and we started to understand how to use them, this was an enormous relief. Finally, the ultimate simplicity.
Right. Absolutely. I understand that in the grand historical context, Feynman diagrams were a massive simplification. But as you might imagine, for the younger generations, we get greedier and greedier as each generation does, and we want something even simpler. So I think the 5-particle amplitude is just an example. You can just see what it is. I wish it could be simpler, and we're just trying to, if you like, raise the bar to make it even simpler. So that's really just the goal for us.
I've also a little question. In the beginning of your talk, you talked about a 3-point diagram on shell.
Yes.
Now, if you put it on shell, you have nothing.
Great.
It's
so
like describing a photon decaying
absolutely.
into 2 other photons.
That's right. So implicitly, I'm working at complex kinematics, where the 3-particle amplitude does not vanish.
Oh.
So what we think about, just like in the analytic S-matrix program of old, the kinematic parameters are complexified, so we can do complex analysis. And in that case, the 3-particle amplitude is non-zero.
Okay, thank you.
So, beautiful talk.
Thank you.
There's nothing in quantum field theory in the basic principles that requires a Lagrangian approach. And one of the advantages of this whole approach is that it's not Lagrangian, although you one has discovered in fact certain things that can then be incorporated in a Lagrangian. But it would seem to me that I would challenge this method to really approach theories which we know exist, quote unquote know, in string theory, but in quantum field theory, such as the so-called 2-0 supersymmetric theory that exists in, we have no doubt, in 6 dimensions, explains upon dimensional reduction incredible features of 4-dimensional gauge theories, including the Standard Model, but has no Lagrangian description. So you have, this approach is a non-Lagrangian approach to amplitudes based on assumed, the general principles and assumed symmetries, and we know what those are for the 2-0 theory.
Right.
Challenge.
It's perfectly tailored to that type of question.
Yes, but so far totally unsuccessful. So what is missing?
So honestly, I think it's just directed effort. So, well, there have been some actual papers on amplitudes in 2,0 theory precisely for that reason, which is that, well, if there's no Lagrangian formulation at all, this is perfectly tailored for it. I haven't thought about it personally. I suspect there's, well, technical, that it's not obvious certainly, but I don't think most of the field's thinking about it. And I agree with you that that is a direction where we can kind of make the most progress, because there's no Lagrangian. There's nothing there. Yeah, I absolutely agree.
So what about fermions?
Oh, yeah, you can include fermions in this whole picture. I just didn't have time to mention.
Not to.
Yeah.
But again, these limit theories, spin a half is obviously allowed. Is there any limit?
Oh, good. So yeah, you can study effective field theories, for instance, with fermions, demanding the same kind of soft theorem, and you can derive the Volkoff-Akrvalov effective field theory for Goldstinos, for instance. You can systematically build fermionic effective field theory. So you can learn, again, old things in kind of a different way in this picture. But I only omitted fermions because of time, but they're absolutely still under this broad brush.